Okay, so this is question 7 in the examples in position versus time graphs. And in this example, we've been asked to draw a bunch of displacement versus time graphs for different situations. So here we have Susie, and she walks to the shop a distance of 200 metres in 100 seconds, takes 100 seconds to buy a loaf of bread, and then walks back home in 100 seconds. So we have our position here in metres and our time in seconds. And we're going to need points at 100 seconds, 200 seconds, and 300 seconds. And we've got up here, we'll have 200 metres. So we have our first point there. Just try and draw as straight as I can. So 100 seconds, we've gone a distance of 200 metres, so our displacement is also 200 metres away from our house, so that's where the shop is. It takes 100 seconds to buy a loaf of bread, so we just stay where we are for 100 seconds, and then we finally walk back home in another 100 seconds. So back home is down here at 0. Okay, so our graph should look something like that, but with nice, neat, straight lines. Okay, so the second scenario, we have Jim. Jim runs from his home to his friend's place. To begin with, he runs at 5 meters a second for 20 seconds. He then has a rest for 10 seconds and then walks for a further 10 seconds at 2 meters a second. Okay, so if you look at your average velocity is equal to s over t, then displacement is equal to v times t. Okay, so if we look at our first displacement, we have 5 meters a second at 20 seconds, so that's going to be 5 times 20, which is equal to 100 meters, so that's the way the displacement's going to be. Has a rest for 10 seconds, so that's easily done, still going to be at 100 meters. Then walks a further 10 seconds at 20 meters a second, so S2 is going to be equal to 2 meters a second times 10, which is equal to 20. But just remember that we have our initial displacement of 100, so it's going to be equal to 120 meters. So I've just added in S1 onto S2. So then we'll have our points. So we've got, let's draw in our axes. So we have S in meters along here and time in seconds. So when did we need it? For 20 seconds. So let's say 20 seconds is here. And we're going to need another one at 30 seconds and then 40 seconds, and hopefully it's not too bad to scale. So we have a couple of points. I'm going to put 100 here and 120 up here. And at 20 seconds we've gone from 0 to 100 meters. We've had a rest until 30 seconds, and then just decided I've got a little bit more energy, I can waddle off now for 220 meters after 40 seconds. Okay. Good. Alright, so question C, we have a car, accelerates from rest, travels at a constant velocity, and then slows down till it stops. No need to give numerical values, so it's actually really similar to the traffic light problem we had before. We were given the graph, so we've got S, T. So accelerates from rest, so this is 0, although you don't need to give any numerical values. Let me just get some different colours here again. So we have 1 here, and it's accelerating from rest, so just remember that's a curve like that. Constant velocity, so a straight line it's not very good. This one's not very nice. That curve should go straight into the into a straight line there. But anyway, and then finally, let's just do green. So 3. Oops. So 3 slows down until it stops. So I'm just going to go curve, and then it comes to rest like that. Okay. So this one, this could be a bit nicer. Like there's not this sudden sharp change. That should just be like that one there should just be like a nice smooth curve into the straight line. But anyway, it should be a nice T there. Okay. Anyway, a stone. Maybe I'll. There we go. So a stone is thrown straight up into the air and returns to the point at which it was thrown. There is no need again to give numerical values. So if we draw in our axes, S in meter, time in seconds. Okay, so we're starting at 0, straight up in the air and turns to the point at which it was thrown. So this is our start and finish point. It's actually a nice parabola like that. Okay, so it's actually being constantly accelerated by gravity, which gives it this nice curve. It reaches a point when it gets to the maximum, it actually stops. So we've got this flat. We've actually got a flat line across around here somewhere. That'll be like a flat. That's the maximum, and it'll be a horizontal line. And then that's when it actually stops, and then it'll start to accelerate back to Earth by gravity, and that's why it's a nice curved shape like that.